Hello and welcome. Today we're going to be talking about the Riemann integral, and we're going to really just focus in this video on one thing, which is defining it clearly and understanding when this integral definition exists and when it does not. We're going to focus on examples and other properties of the integral in a later video. Okay, so let's now define what we mean by an integral, and we know the goal was to find an area under the curve f of x is equal to y and the y-axis. For this video, we're going to, of course, assume that f is greater than or equal to 0. And, of course, we want to under the y-axis, and we're also going to look over an interval a comma b. All right, so I can draw a picture. Here's some f of x. And there are my axes right there. We have an a, and we have a b. And again, we'll assume for this video that f is greater than or equal to 0 for that interval, and we'll discuss what happens when that's not the case in a later video. Okay, so in order to figure out what this area is, what we want to do, of course, is we want to figure out what this area is, and we've talked about in previous lectures. The idea, what we're going to do is, of course, we want to start with a partition sequence. So what we're going to do is we're going to define a set xi, where I goes from 1 to n, and this partition sequence is going to be defined by a parameter n. And that parameter n then basically says that we're going to start at xi, x1, and we're going to go to x2, we're going to go to x3, all the way to xn, okay? And we may, in fact, include, I'm going to actually do this. We'll start at 1 and we're going to start at 0 and go to 1, and then 2, and then 3, and then so on and so forth, all the way to xn, like that, okay? And so the partition will always have n plus 1 terms. Okay, and these xi, all of them, are going to be inside the interval a to b. And x0, we can actually say this. I'll just say that x0 is going to be a, and it'll be, of course, the start. And, of course, xi is always going to be less than or equal to, we'll say it's actually strictly less than, xi plus 1, okay? So each different term is going to ascend up, and then, of course, that xn, that'll be b. All right, and basically what this does, of course, is just split up our interval into n plus 1 different points. And in it, we have, if I look at all the intervals there, in between the points, we have n intervals. Okay? Okay, and that's why we call it a partition. Okay? It's a partition of a to b, meaning that we've broken up that interval into those pieces. All right, and again, the idea, but I said that we were talking about this thing called a partition sequence, right? And the idea here, of course, is when we're talking about a sequence, is we're going to take we're going to allow ourselves n to increase. And of course, what we're going to do, of course, is we get more subintervals. And they're going to be closer together. or they're going to be, I shouldn't say that they're closer together. Rather, what I'll say is the intervals are going to be, they're going to be smaller intervals. Okay. One thing we're not going to do, because we're talking about this integral in the most general possible way, is let's say how we choose specific points. Xi, we don't specify. Okay? We're just going to assume that we're going to do this, and you might choose different ones than I will. But we could actually now think about a specific example, of course. A specific example might be a very simple one, which is basically even spacing. An even spacing, which is going to be, maybe if I'm going to do it this way, maybe I'll say, well, I'll just give an example of xi then could be equal to, I can take my whole interval, the whole length of the interval, right? And then I'm going to multiply it by I over n. So that gives us a nice even spacing. So however long my interval is, like that, from A all the way to B, I'm going to have nice even spacing, a nice grid, if you will, all the way through. So here, x0, we can see clearly that x0 is actually going to be, oh, sorry, I forgot one thing. We have to go plus A there. So let me just erase that box there real quick. Plus A. Okay. So x0, of course, is going to be, if I plug in I equals 0 to this expression, I get A, right? And then, of course, the next one is going to be x1 is going to be A plus B minus A over n, like that. So that's just a little bit bigger. Right, and if I keep going, if I go all the way to xn, I see I'm going to get an A plus B minus A all over n times n. Those are going to cancel. And it's going to be A plus B minus A, which of course is B. So we get to the final ending point. Right, one thing I want to do there is look at basically each one of these is going to be even, which means, of course, they're going to be the same width. Right, so we can even give this a name. We're going to call that delta x. And generally, they could be different widths, but we'll say that they're, in this case, the even spaced example, they're going to be the same width. That's actually going to be that increment, b minus a over n, in this particular case, is going to be that increment we advance. Okay. So we can do this now, of course, for every possible choice of partition, but we gave you this simple example of the even spacing one. But in principle, we should be able to choose other irregular spacings, and that should work just fine. And the idea here is we break up our interval into these pieces like that. And then the final thing we need to check is, and then we'll break it up into these little stripes like this. And the final piece of ingredient to this thing is then we have to also choose a representative point. We're going to call that xi star. And these are representative points, I should say. And I, the set, is going to be from I from 1 to n, so there's n of them. x1 star, x2 star, and so on, like that, okay? And these set of representative points are basically just points in each subinterval of the partition. Okay? And if I put that up on my graphic that I have here, so I'll do this in a different color. So first, actually, I'm going to put, there's my x1, there's my x2, x3, all the way up to xn up here. And now in blue, I'll say I'm going to pick some representative point there. That'll be x1 star. And here it could be x2 star, x3 star, and so on like that. And the idea here is that we're going to take that point, move it up, and find the value f at that point. So I'll call that f of x1 star right there. And if I take that to be the height, then that will be, the area can be defined thusly. The same thing here, as I can move that point up here. And from there I get f of x2 star. And now I see that will be the representation of the area. Likewise here. If I choose another point right there. So you can already see that in some cases I'm over or underestimating the true area under the curve at each of these points. But remember, what we're doing here is we're clearly coming up with an approximate area of this under this curve. Okay, so now let's put this all together, and I'm going to have to go to a new page. So what I'll do is I'll draw another one of these graphs, f of x here, from A to B. Draw my partition, and then draw those representative points within the partition, like that. And they can be, and the representative point can be any point at all in the interval, and it could even be the endpoints of each interval. There's a lot of flexibility in the choices you have on how to find these. Right, so we see here we're clearly missing some of the area. So clearly there's some error there. But we're not going to worry about that because we're just setting up the approximation. So again, let's summarize. We choose the partition. Xi. And it goes from I equals 1 up to n. We choose the xi stars. I goes from 0 to n, and here I goes from 1 to n. I misspoke there, right? We choose those x stars, and then what we do is, of course, we generate those heights, f of xi star. And here, of course, we generate the interval widths. So we have the delta xi, which is going to be equal to delta, or xi plus 1 minus xi. Okay. And then what we're going to do is we're going to say the area is approximately the sum from I equals 1 up to n of the heights of each one of these rectangles times their base, their width, like that. All right. And so, of course, the idea is, of course, if I take the limit of n going to infinity of these sums like this. So in this case, I need to make a comment here at each increasing n, we must create a new partition, a new set of representative points. Also, we need to require let me erase that require and rewrite it, that the delta xi, they all go to 0. Okay? And in fact, a lot of people even write that under the limit sign. They say the delta xi's all go to 0, just as a requirement. You can imagine I could pick partitions in a certain way that I keep increasing the number of my partitions, but maybe I keep a few of them big and I let them stay big forever. Well, we don't want that. We want every single one of those little bars to get skinnier and skinnier. So the idea here is that basically each base times height has a base that's going to 0. So we're going to define this to be this new symbol from a to b of f of x dx. And here the idea here is the dx equals the limit as the delta xi's and going to infinity all go to 0. But the idea is that we're taking that limit as them going to 0, but they're not ever quite 0, right? All right, so again, this symbol, we need to make a qualification here that this is equal to some number. That, of course, is the area under the curve. And the idea here is that as the partitions get finer and finer and finer, all those little over and under approximations all go to 0. We no longer have those areas because our partitions get narrower and narrower, and we're able to fill in all of that area through the whole thing. So that is the definition. So one thing we're going to say is that this object here, when this limit exists, we call it a Riemann sum. Okay, and this Riemann sum obviously is named after a person called Riemann from long ago. This Riemann sum, okay, it has to exist for every choice of partition and xi star, we can dream up. Right? So it has to be flexibly defined, right? Okay, and it has to exist. Otherwise, we're going to say that the Riemann sum fails. It fails to exist. And we're going to say that this symbol, of course, would be the limit it must exist for this symbol, this integral symbol, to exist. And we call this, of course, a Riemann integral. Okay. And again, it is a number value of the Riemann sum's limiting value as our partitions get larger and larger and larger, and the partition widths get smaller and smaller and smaller, and we relate this to the area under a curve. All right, so let's just get practical for a second here. I'm going to go to the next slide. Okay, so now we know that the sum must exist. The sum must exist, and, well, let me back up here, actually, and be a little bit more clear with my language. The approximate sums, and what I mean by that is the finite ends, the finite end sums must all get values closer to each other for every possible choice of partition or xi star representative points. All right. So, and by we say closer to each other, we should highlight this is basically how we define that the Riemann sum limit exists. Okay. So again, I'll write down the integral from a to b of f of x dx. This symbol represents this process of n going to infinity and delta xi all going to 0 of this finite sum like that. Okay, so if this is the definition, and again, that's only if it exists, what we want to ask is, for what f of x, x's, and intervals a, b, can this sum limit, the sum limit, exist? This turns out to be a very hard question, but let me just summarize it as a theorem. So the theorem is if f of x is continuous, on the interval a to b, or if it only has finitely many jump discontinuities, then then any choice of partition sequence and representative point sequence will yield a valid Riemann sum. And therefore, the value f of x, the integral of f of x dx exists. So I'll put that with some exclamation points. That's very nice. So that theorem covers a lot of ground, and let's see if I can take a second to define what we mean by this. You know, what's the meaning of the theorem? The meaning of the theorem has a lot of, it actually makes things very practical. As long as f is continuous, or at least continuous enough, if f is continuous, it means we can choose a very simple partition. For instance, we can choose the even-spaced one. xi equals b minus a over n times I plus a, and we're going to have delta x I just be simply b minus a over n, and we can choose the left endpoint. So xi simply equals xi star simply equals xi minus 1, okay? Or the right endpoint, xi star equals xi, or the midpoint, or actually any other point in between as well. All will work. All right. So what I would say here, of course, is that all will work and all will lead to good approximations that get closer to the true value So what we can say here is that the sum I equals 1, I should say as n gets large. So for any finite sum, this is going to be approximately equal to this value that's out there. We may not know what it is, but we can say with some confidence that that at least we know we'll get close. And if you want to get closer, just take a finer and finer partition as we go forward. And I'll make one more comment here, is that in most scientific applications, or engineering applications, this partial sum, or this I shouldn't say a partial sum, this approximate sum. This approximate sum is the best method for computing integrals. So the choice of how we perform the sum, whether we use left endpoint, right point, midpoint, and I should also mention there are more complicated or more detailed algorithms out there. But what we're saying here is that integration, for any practical sense, becomes a matter of computer programming. To compute an approximation. Okay, so I hope that gets you a clear sense of an integral and how it's defined. I know we haven't done any very clear examples here, but I wanted to get that theorem out there, and it says that not only that it needs to work for any partition, but as long as you have a continuous function, you're guaranteed that any choice of partition will work, so you can choose a convenient partition to use in order to compute. So an integral existing requires a very heavy requirement that any partition will work, but it turns out that as long as you have a continuous function, you're guaranteed that it will. Therefore, you can choose a simple choice for how you break up the intervals into small pieces and compute those areas. All right, so in the next video, we'll do a few examples of these Riemann sums, and in subsequent videos, we're going to show you more properties of the Riemann sum. Thank you very much.